Hello everyone and welcome back to Things You Should Remember from Strength and Materials, but I've likely forgotten. In this one, we're going to start with combined loading, and we're going to finish off with two elements that you see on our structure there, H and K. This example is a made-up one, so if you want to work in it on your own, your numbers will be, some of the numbers will be really large and some of them will be really small, all still within the megapascal range, but I'm getting upwards of 900 in some cases and as low as 2. So I should have done this a little bit better beforehand, but it is what it is. This is all about the process. So first things first, we have to take our forces from where they originally are and bring them to the cross section that has elements H and K. I'm going to be using red for Y, blue for X, and green for Z, just to try to keep things consistent and a little easier to follow. So first things first, we have to move them and create our moments as well that are caused by the forces. And this I try to show as many people as I can. When you're doing moments about Z, you need forces in Y, distances in X. When you need and forces in X and distances in Y. Notice that they each pair up, and when it's Z, it's YX. When it's Y, it's XZ. When it's X, it's YZ. Every element, or how should I say this? Every axis is used. If you're looking for X, you need YZ. Y, you need XZ. Z, you need YX. And so taking our forces from where they originally were and bringing them to there, using the black arrows around our axes as what I'm defining as positive. That's why moment about X is negative. It's just opposite of what I've called positive. But either way, filling in for all of our distances and all of our forces, we get our moments. These are the moments that we bring to the cross-sectional area where elements H and K are. And so we get to this. This is our force moment system that we learned back in statics. Should be relatively quick, but it's still something that we need for machine design. And so each force and each moment will cause a single stress each. It may be a normal stress, it may be a shear stress, but it's always one-to-one. And I've labeled them here. And what their forces or what their moments are replacing. So in the case of Fy in the top left, we have the horizontal shear VQ over IT. That Fy is going to be replacing that V, and so on. Now, what I like to do first is figure out which of these I'm going to be calculating, and then figuring out what geometric variables I need to calculate, such as these. First moment area Q for my horizontal shear, first moment of inertia I for multiple things, polar moment of inertia for my torque, area, radius, and thickness. A side note for Q, specifically for a circular rod or a circular cross section, it is equal to 2/3 r cubed. In fact, all of these are related, or all of these formulas have been for a circular cross section. But just a side note for Q, the actual formula is A times Y bar, and I've gone through a little bit of a proof to see why we get to 2/3 r cubed on the side, where A for a semicircle is pi r squared over 2, and the Y bar for a semicircle is 4r over 3 pi. Some things get eliminated, fractions reduce down to 2/3 r cubed. For radius, of course, that's r. Thickness T is our diameter. Since this shear force, or the horizontal shear force specifically, will be going through the entire cross-section from left side to right side, or just from one side to the other, it will take the entire diameter, which I believe was 30 millimeters. So that's also a thing to note. And then, of course, here are all the completed numbers, all in meters. Oh, in some variation of meters, meters squared, meters cubed, meters to the fourth. And then substituting all of our forces and our moments and our geometric variables in, I get these numbers. So I was explaining at the beginning that I did get some very large and some very small numbers. Again, I made this one up on my own, but it's more about the process than the final numbers. but here they are. Now for the tough part of figuring out which stresses affect which element. Typically, when I do my homework, I will create this kind of table and kind of explain to myself which elements are affected by which force. First, I'm going to start by the stresses that cause, or the stresses that are affecting both elements, and that will be our axial force sigma z, which was P over A, and our torsional shear force tau z, both affecting the elements. In the case of the normal stress, it's causing tension. In the case of the shear stress, it's causing shear. We'll get to directions a little bit later when we bring it all together. Next, we have our bending moments. These, of course, create that Z pattern that we're familiar with from strength of materials, where one side from our neutral axis is in the maximum compression and the other side is in maximum tension. In the case on the top one of stress caused by the moment Y, element K is affected, and only element K. Element H has zero stress caused by moment about Y, and element K is in compression from this. Similarly, for stress caused by the moment about X in blue on the bottom, element H is in maximum compression, and element K is not affected, and I reflect these findings in the table on the right. And then finally, we get to our horizontal shear. Now, the horizontal shear takes a bit of a parabolic kind of shape in the stress profile, where at the top and the bottom, we call those free surfaces. They have zero stress. However, at the centroid, that's where the shear stress is maximized. And it should be noted that the shear stress is in the direction of the force. So for the red Fy, it's going along the positive axis and up, going from the bottom to the top on the left side of K. And for our blue horizontal shear caused by Fx, it'll be going down from top to bottom across the left side of H. And so now that we have all of these together and what's affecting what, we can begin to build our elements like this. Now, each stress comes with a opposing stress of equal magnitude. What does that mean? It's simply what we do to make sure that it's equal and opposite on both sides. That way we're not having a major stress from the left and nothing from the right. This needs to be statically determinate, so it needs to be balanced on both sides. So you'll see that the normal stresses in both black and red are opposite each other. And for the shear stresses in the corner, there are two pairs. The greens match up with each other and the blues match up with each other. The way we determine which one we'll be using is we'll do a little bit of math to see which one is greater. And I'll go into detail about that in the next slide. But as soon as one arrow is valid, all of the arrows in that same color are valid. So if we find that we're all in the green on the left side going down, all of our green arrows are true and are valid, and the blue arrows, we just determine that it's the green arrows, the shear in the green direction. So we're going to start with element H, and I've made the orientation here of where it is on the ZX plane and where the positive Z and the positive X axes are. The very thick line on the left side, I've denoted that as where that slice is. The open face that we did our force moment system to is on that thicker line. And this comes in handy when we're trying to calculate our shears. So if we look back, I'm going to scroll back to the torsion here on the bottom. We're looking at element H. It's going from left to right, or from right to left rather. It's going along the negative X axis, and that is reflected here. Tau Z is our shear caused by torsion. It is going in the opposite direction of X. This is how I determine which way my shear is going. I look at just that face and I observe which direction the shear is going in relation to that face. Similarly, if we go back to here and we see element H on the bottom, the transverse shear is occurring in the positive x direction from top to bottom. And that is reflected here. If we look at the bottom of the element H on the top, we see that the horizontal shear from x is going from top to bottom in that same direction. This is how I determine which direction my shear stress is going. And then we have to do a little bit of algebra. Again, some of my numbers are huge. It is what it is. We're just going to work with it. So we find that the normal stress, the total normal stress, which we can add and subtract as just regular numbers, our total stress is 978 megapascals in compression, and our shear is 220 MPa. Since tau z is bigger than tau Vx, it's going in the direction of tau z. Once we've determined it's in the direction of tau z, we can confirm all of the other arrows to match that direction. And now for K, we do the exact same thing. We observe which direction our stresses are going, both normal and shear. In this case, our shear is going in the same direction, so it's a little easier. But we can refer back to these slides on the directions of our stresses, and then we can add them linearly to get our values. So in this case, for K, our horizontal axis has a compressive stress of 506 megapascals, and we have a shear of 233 megapascals. Now, technically, this shear in this orientation is negative. We don't need to worry too much about negative or positive. We just need to make sure that we get our directions right. And in the case of this, both of our shears actually are corresponding with the blue arrows instead of the green arrows. If we had the green arrows, we would technically call it positive shear, but once again, we don't need to worry too much about that positive versus negative. We need to make sure that we get the directions correct on our element. And so to finalize things, we get all the way down to our two elements, H and K, and the appropriate values. In the next section, I'm going to go over finding our principal stresses and using Mohr circle, which is the final thing from strength of materials that we will need to complete Machine Design 1. Thank you, everyone.